Hello, everybody. Good morning. Or maybe I shouldn't say that. Hopefully, you're watching this on Wednesday morning, but I know a few of you are taking the PSAT on Wednesday, which means you are probably not watching this right away on Wednesday. Your brains are fried and you are ready to go home and relax on Wednesday afternoon, and maybe it's not until Thursday or maybe even Friday that you get around to this. But whenever you are watching this, we're going to pick up where we left off. We were doing compound growth using the formula that you see on your screen. And so just a refresher of how that worked, I've got a simple problem to get us started off. If I have $5,000 today in an account that pays 7.2% interest compounded monthly, how much will the investment be worth in 13 years when my son starts college? At this point, I'd like you to try this one out on your own. So I will give you a chance to pause this, and I'll come back in a moment and show you what to do. But go ahead and pause the video. And you are unpausing because you've all finished the problem. So let's take a look at this one. We're plugging stuff into the formula. 5,000 is my principal. The R value is 0.072. Move the decimal point over 2 spots. This one is compounded monthly, so N is equal to 12, and we're going for 13 years. Make absolutely certain that when you try to plug something like this into your calculator that you are plugging it in right and getting the answer that I've got shown down on the bottom of the screen, $12,713.20. If you're not getting that number, take it in smaller chunks. 0.072 divided by 12, take whatever that is plus 1, figure out what 12 times 13 is, and then take that previous number and raise it to that power. But break it down into small chunks and do not round unless you absolutely have to. Leave it as the number that's in your calculator. You've got this big, powerful calculator that can do big, powerful calculations. Well, that's what we were doing. To move into what we are doing today, the new stuff for today, it's actually a really interesting formula that we're going to be coming up with. And to introduce this, I always use this preposterous situation. This is absolutely crazy, absolutely ridiculous that something like this would ever happen. But imagine that you got $1. Yes, $1. And you're going to find an amazing bank account that pays you 100% interest. That's where this gets preposterous. You'll never find a 100% interest bank account, but just pretend for the sake of this problem. You'll see why in a moment. And we're going to have this invested for 1 year. So using the compound formula, we are going to have 1 for the value of my principal. We're going to have 1 for the value of R. And we're going to have 1 for the value of t. And that's why I'm going with this, so that everything is as simple as possible, just plugging in 1. And my only variable is the value of n. We're going to have 1 times 1 plus 1 over n raised to the n times 1 power. And we're going to see what happens as the value of n increases as we compound this more and more and more frequently. So if we were together in a classroom, I would take every individual row and I would assign you a different number of compoundings. I would say, you over there against the window, I'd like you guys to do this for n equals 1. And for those of you over by the wall, we're going to let n equal 2. And that group over there that's sitting under the clock, you're going to do n equals 4 for quarterly. I would break this up. Gosh, maybe if this was a Zoom meeting, I could send you out into breakout rooms and you could all stare awkwardly at your screen because everyone's afraid to talk for 15 minutes. But maybe someone would actually go through and do this. And so you'd plug in all of these different values of n, 365 for daily, 525,600 for every minute, into this formula and see what happens. Now, we can't do that today. I would encourage you, again, I'm going to pause for a moment and say, plug in one of them. Pick one of these numbers to plug in. Maybe choose daily. Plug in 365, see what you get. Plug in 12, see what you get. Go ahead and pause. And I will resume because you've all done at least one of these calculations. And so hopefully you got one of these answers. If you compound once at 100% interest, your money doubles. So you got $2 now. Twice a year, you get an extra quarter more than you would have gotten if you only do it once. And we can see that as the number of times we're compounding goes up, the amount of money that we're making goes up also. Like we saw on Monday, we are compounding, we're getting a little bit more money, and we're getting a little bit more interest on that little bit more money. But look at what happens when you start getting to really large numbers of compounding. From 1 to 2, we gain a quarter. From daily to hourly, from 365 to 8,760 times compounding, we only gain 1 cent. And that's the last cent we gain, is as we go from every hour to every minute to every second, the difference is so small. There is a difference, to be honest with you, but we just don't see it when we round to the nearest cent. In fact, I know that this will never get above 2.72 for a reason that I'm about to show you. It turns out that as this number increases, as the number of times compounding, so the graph you're looking at right here is the graph of this function, y equals 1 plus 1 over x raised to the x power. And as the x value increases, we see that the y value increases fairly fast at first, going up a quarter, only going from x equals 1 to x equals 2. And as we continue to go higher and higher, this levels off. And if you graphed this far to the right, x equals, instead of 80, 800, 8,000, 8 million, there's an upper level. There's a number that this is approaching, somewhere between 2.6 and 2.8. And it turns out that that number is the number E. Now, if you've been paying attention to my videos, you've seen that I have an E poster in my background. You'll have to watch for that when I see you again next Monday. But that poster has the number E, which is similar to the number pi, a non-repeating, non-terminating decimal, 2.71828182845904523, blah, 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 blah. Again, a number like pi that comes from this situation, sometimes known as the natural exponential, also known as Euler's number. That's why the letter E is used to stand for it. We are going to use this to deal with continuous change. Basically, if we take the number of times compounding and let it go not just to a few million times per year, if we're continuously compounding, if we are always compounding, what is the number that approaches? It turns out to be this number E. Now, what that means for us is that this complicated formula that you used for your homework that was due today becomes actually simpler. This formula, if we say we're compounding all the time instead of once, quarterly, monthly, if we say we're compounding continuously, it actually cleans up and looks like this. It's just the same principle times e to the interest rate times t. Now, the mechanics behind how that works and how this equation transforms is a little bit higher level than we're ready to deal with, but it's a fact. And you can try it with some numbers and investigate and see. We kind of already did with what we looked at with $1 at 100% interest for 1 year. But anyway, this is true. This is a true fact. You're probably going to remember this formula as the Apert equation. I repeat, you'll remember this one as the Apert equation, one of those equations that most people actually remember because the mnemonic device literally says what the formula is. Apert, A equals P times e to the RT, where E is a number that is on your calculator. On your calculator, it shows up in two different places. I'm looking at my calculator. It's the second function of your division button if you've got a TI-84 calculator, or over next to the 7 and the 4, there's also a second function that does e to the x. One of them that's by the division button, that's just the number e. But if you go with the one that's by the 4 and the 7, it'll actually raise e to the power. So play around with those, experiment, and here's our chance to do that. Let's take a look at a couple example problems. I've got $1,000 invested at 8% compounded continuously. That's a key word. As soon as you see this word continuously, I want you guys to write down the equation. You'll do a better job than I will, apparently. The amount is equal to the principal times e to the RT, where 15 years is my time 8% is my rate. Of course, we'll put 0.08 in for that. And 1,000 is my principal. I plug that in. Plug this in your calculator carefully. 0.08 times 15. I might plug that in my calculator first, and then do e raised to that power, and then finally multiply by 1,000. You should get $3,320.12. If you don't, go back and look at how you're plugging it into your calculator. Watch your parentheses, watch your order of operations. Okay? Next example I have is another one. This is not just simple exponential growth. This is actually something that comes from a formula that Newton invented. But he figured out that this relationship exists for something with a temperature that is higher than the temperature of the surroundings. Take a moment and read this one. So we're given a function, temperature as a function of time. And so if I want to know what is the temperature after 45 minutes, I just plug in that time, plug in the 45 for the value of T, and everything else is given in the formula. So plug things in and make sure that you're plugging these things into your calculator correctly. Personally, I would do negative 0.02 times 45, raise e to that power, then do multiply by 75, and then finally add 20. And so make sure you can get 50.5 degrees for that one. And then one final problem for us to look at. In 5 years, it'd be awfully nice if I could buy a new car. So I've got my eyes on this Audi R8 V10, which seems like it's right in my price range. It only costs hopefully about $175,000. And so I'm going to go through my couch cushions tonight. I'm hoping to get about $125,000 by going through my couch cushions. So I'm wondering if that's enough. If I put it into a bank account at 7.25% interest, will it be enough if I've got an interest or a bank account that compounds continuously? So take a moment. Again, I'll pause or give you a chance to pause, and then I'll come back and explain how to do this one in actually 2 different ways. So take a moment, pause the video. And as you are resuming, hopefully you are plugging things into the formula. I'm guessing that some people maybe did something like this. The final amount on the left side, principal times e to the interest rate times time. And this is a little bit of a problem because this isn't true. There's nothing to solve for. There's no variable here. I just have something that's not exactly true. The left side is not equal to the right side. Plug in the right side and you'll find out it's not 175,000. Because this question is asking, is it enough? If I start with 125,000, will that be enough to get up to 175? Or if I need 175, is 125,000 enough? So basically, we need to leave one of these off. So I'll show you a couple different ways. One way would be to say, I don't know what the principal is. I need this much money. So how much principal would I need to start with in order to end up with 175,000? So if I do that, easy to solve for the principal, I'll just divide both sides of the equation by e to the 0.0725 times 5. Again, please be careful how you plug this into your calculator. I would do 0.025 times 5, raise e to that power, and then do 175,000 divided by that number using my calculator. Make absolutely certain that when you do this, you end up with the number that I've got here, $121,788.50. Which means that's how much money I would need. Since I'm starting off with more than that, looks like my answer is yes. It looks like I've got enough money. But this is actually the hard way to doing this problem. Hopefully some of you tried it this way and said, okay, if I have this amount, 125,000, I can figure out what the final amount will be just by plugging it in. And so you plug this in, plug it into your calculator. Again, make sure that when you plug this in your calculator, you get this. If you don't, if you're trying and it's just not working, I would again say make sure you're not rounding. Don't round anything off unless you have to. And if it's still not working, well, you'll have to ask me about that on Monday when we're working together on this one. But just be careful how you're using your calculator and plugging numbers in. I'm getting the same answer. I have enough. This initial amount is enough that I'll have more than $175,000. I've even got $4,600 extra dollars. I can use that to upgrade the stereo or something like that. So There we go. That is continuous growth. If there are questions, we can certainly take a look at them on Monday. We'll have time for questions on Monday. Really, the only point of Monday, or I shouldn't say the point, but the goal for Monday is working with real world situations, kind of like we've been doing. So it shouldn't be too much to add on to what we have been working on. And then we will review and get you guys ready for the next quiz that's coming up right away. Make sure that you've got a calculator. Make sure you've got a functioning calculator that you know how to use. Don't borrow one from a friend on Wednesday, because if you don't know what you're doing on the calculator, you're going to get some wrong answers. So I will stop there. Certainly let me know if there are any questions. But yeah, that's it. Have a great MEA break. Or if you're doing this late at night on Sunday night, then shame on you for procrastinating. But I hope you had a wonderful MEA break, and I will see you again on Monday. Bye bye.